Hello one and all, welcome to another online video by Einstein Academy. In this video, we'll be looking at learning outcome C from the topic of chemical bonding from the JC H2 chemistry syllabus. Learning outcome C states that candidates should be able to describe covalent bonding in terms of orbital overlap limited to S and P orbitals only, giving sigma and pi bonds. So in this section, we'll be purely looking at how covalent bond forms. So previously we mentioned that a covalent bond is formed due to the sharing of electrons. However, how can the atom come to share their electrons? And the way they do so is to form covalent bonds, and it's formed by the overlap of valence atomic orbitals where two atoms approach one another to share their electrons. So basically, right, what happens is that one atom uses one of its orbital to overlap with the orbital of another atom to share a common space, and in that common space, they will put their electrons to be shared in the overlap of these orbitals. So like a pictorial view of this will be shown in the next slide. So I hope that is clear. So there's two, but the thing is that in order for the orbitals to overlap, there's actually two ways that they can overlap. It's either head-on overlap or side-on overlap. And this will result in the formation of either the sigma bond or the pi bond. So if we were to look at the sigma bond is formed when the two atomic orbitals from the two different atoms overlap head-on. So head-on is like this, okay? Head-on overlap and not sideway overlap. We'll look at the sideway overlap and then everything will be clearer. What's the difference between head-on and sideway overlap? So if you look at there are a few ways to form sigma bonds. One of the ways, if like, for example, if you have two hydrogen atoms, then the s orbital of one hydrogen atom can overlap with the s orbital of another hydrogen atom, and this will be the common space of, this will be the overlap region, and they will actually put both their electrons to be shared in this region. And the attraction, I remind you again, the attraction between the nucleus and the shared pair of electrons, that is the definition for the covalent bond. It's the electrostatic attraction between the nucleus and a shared pair of electrons. We can also have an head-on overlap between a s orbital of the hydrogen and a p orbital of the chlorine. So I hope that you can see that this is a head-on overlap. It directly collides again once, it directly head-on approach with one another. And then like, again, we can put the shared pair of electrons in this region. Or the final case, at least the final case in the syllabus, is the overlap between two orbitals. And this is the overlap region whereby they can place their shared electrons inside here. Okay, so this is the sigma bond whereby the orbitals overlap head-on. The pi bond, on the other hand, is when the orbitals overlap sideways. So, and this only happens between two p orbitals, because like for an s orbital is spherical in shape, so there's no such thing as the sideway overlap. So a sideway overlap can only occur between two p orbitals, and this is a sideway overlap, okay, instead of a head-on overlap. And again, this is the overlap region, and then they can place their shared electrons in the overlap region, and this will result in the formation of the pi bond. Okay, so the thing is that single bonds are always sigma bonds. So for example, if we have a carbon-carbon bond in this manner, let's say we talk about the ethane molecule, this carbon-carbon bond will be always, if it's only a single bond, it will always be a sigma. It will always be a single bond. Sorry, if it's a single bond, it will always be a sigma bond, head-on overlap. However, if we have a double bond, such as this molecule in ethene, okay, this one is a double bond, and okay, sorry, let me just highlight this. This will be one sigma bond. This, because it's a double bond, and the double bond is two bonds, right? One of them will be a sigma bond whereby it's a head-on overlap, and the other bond will be the result of a sideway overlap between two p orbitals. One p orbital on this carbon and the other p orbital on this carbon. On the last case is where we have a triple bond. If you have a triple bond in this case, then again, the first bond will always be a head-on overlap, which results in the sigma bond. And the other two remaining bonds will be two pi bonds, where it forms as a result of the sideway overlap between the p orbitals on this carbon and the p orbitals on this carbon. We will see the pictorial view of this in the few later slides. In terms of bond energy, the triple bond is stronger than the double bond, which is stronger than the single bond. So if you look at the triple bond, right, there's actually 3 pairs of electrons that is shared between this carbon and carbon, and hence the attraction between the nucleus and 3 pairs of electrons must necessarily be stronger than the attraction between the nucleus and 2 pairs of electrons, which is stronger than the attraction between the nucleus and only 1 pair of electrons. And hence, it must be true that the triple bond is stronger than the double bond, which is stronger than a single bond, and it will require more energy to break the triple bond as compared to break the double bond as compared to breaking the single bond. And therefore, in order of bond energy is in this order. Again, the triple bond stronger than double, which is stronger than the single bond. Okay, now we would like to talk about the concept of hybrid orbitals. Consider the ethyne molecule. So this, if you look at ethyne molecule, right, how many electron domains are there around this carbon? This will be properly covered in the next learning outcome, but I have to talk about this before I can talk about why hybrid orbitals form. So if you look at the dot and cross diagram for this carbon, right, there will be 3 pairs of electrons in this CC triple bond, and then there'll be 1 electron here, which means that, right, there are actually 2 electron domains around this carbon atom. And as we mentioned previously, right, the way that we want to, the shape of the molecule is always adopted such that they maximize the separation of the electrons to minimize repulsion, so that it will result in the most stable configuration of the molecule. And if we have 2 electron domains, such that, like for example, if we got 2 guys that we want to separate around this carbon, right, the best way is to separate them such that they are 180 degrees apart. There is no way that you can place the A and B in another configuration such that A and B is actually further away from this configuration of 180 degree separation. And as a result, right, if you have 2 electron domains, the geometry around this carbon must be linear, and around this must also be linear, and hence the entire molecule is linear in shape. So this bond angle is 180 degrees to minimize the repulsion between all the electrons of the molecule around this carbon atom. If we were to consider the ethene molecule, right, if you look at the number of electron domains, right, how many set of electrons are there around it? And the answer is 3, 1, 2, 3. And again, you can show mathematically that the maximum separation that you can separate 3 electron domains is in a 120 degrees manner. And as a result, the shape of this molecule, the bond angle between the HCH and the CCH is all 120 degrees. And this again is to minimize repulsion between all the electrons of the molecule. For the methane molecule, the carbon atom is bonded to 4 hydrogen atoms, and if you count the number of electron domains around the central carbon atom, you will realize that it's actually 4. So 1 set, 2 sets, 3 sets, and 4 sets. And again, you can show mathematically that the way to maximize the separation of 4 electron domains in a 3-dimensional space is in a tetrahedral arrangement. If we are living in a 2D world, right, then the maximum separation that you can separate 4 things would be like that, whereby it's 90 degrees. However, I hope that we all can agree that we at least live in a 3D world. We actually live in a 4D world due to Einstein's special theory of relativity. But like for this purpose, we can just say that we live in a 3D world. If you live in a 3D world, then the maximum separation is as such, whereby like this H and this H are in the same plane, and then this hydrogen is coming out of the plane of the paper, while this hydrogen is going into the plane of the paper, and this is a tetrahedral arrangement. And mathematically, it can be shown that for a tetrahedral arrangement, the HCH bond angle is 109.5 degrees, and this will maximize the separation of the 4 electron domains to minimize the repulsion between all the electrons, which will result in the most stable shape of the methane molecule that it can form. And so why are we talking about these 3 molecules? Why are we talking about the ethyne molecule? Why are we talking about the ethene molecule? Why are we talking about the methane molecule? The reason is because we want to introduce the concept of hybrid orbitals. So let's consider the shape of the methane molecule, right? So this carbon and this hydrogen, and this carbon and this hydrogen, this bond angle is 109.5. But if we look at the orbitals on this carbon, right? Remember the carbon valence orbital is made up of a 2s orbital, and you have 3 times of the 2p orbitals, and they're in this configuration, right? You have a sphere, and then the p orbitals, one of them lie along the x-axis, one of them lie along the y-axis, and one of them lies along the z-axis. And remember when we say that covalent bonds are formed, it will either only be head-on overlap or sideway overlap. If it's all hit-on overlap, right? I hope that we agree that, like, for example, if you overlap with your s orbital here, and you overlap with your s orbital here, and you overlap with your s orbital here, the bond angle between the HCH, right, can only be 90 degrees. There's no way that we can achieve a 109.5 degrees bond angle because of the configurations of the p orbitals being 90 degrees to one another. So, like we meant, it's also impossible to achieve the 120 degrees bond angle in the ethene molecule, because by virtue of the fact that the p orbitals on the carbon is actually 90 degrees apart, and orbital overlap can never ever create a separation of 120 degrees. So it's impossible to achieve the bond angles of 180 degrees, 120 degrees, and 109.5 degrees with the original s and p orbitals. So what is the atom solution to this? Okay, so let me state the problem again. Orbital overlap will result in the formation of covalent bonds. The ideal bond angle that we would want in certain molecules is 180 degrees, 120 degrees, and 109.5 degrees. However, existing p orbitals, which is separated at 90 degrees, is unable to form bond angles of these bond angles if they were to use the original p orbitals. So the atom solution is basically to take the s orbital and some p orbitals and kind of like take it in, break it down like plasticine, and then remold them into new set of orbitals that point in the correct orientation, such that when they achieve orbital overlap, they can create the correct bond angles of either 180 degrees, 120 degrees, or 109.5 degrees. So depending on whether you want to create a bond angle of 180 degrees, 120 degrees, or 109.5 degrees, you will take the remolding process will involve a different numbers of s and p orbitals. So there are three possibilities, because there are three possible bond angles that we want to create, right? Hence, there are three possibilities in which we can remold the s and p orbitals to achieve these bond angles. The first of which is the sp hybrid orbitals. So the way to understand this sp hybrid orbitals, right, is basically like we take in one of the s orbital and we use one of the p orbitals, and so like one s orbital and one p orbital, and I'll take it in and remold it into two new orbitals, because I took in two orbitals, right? Which means that when I remold it, I will also result in two new hybrid orbitals. These are the remolded orbitals, and the terminology for the name of these hybrid orbitals is the sp hybrid orbitals, because of the fact that we use one s and one of the p. And the orientation of the shape of the sp orbital looks like this. That it will be directional in the sense that there will be a bigger loop in one direction and a smaller loop in one direction. So this is one of the sp orbitals, and this one is the other one of the sp orbitals, and it's at 180 degrees separation. So when this orbital overlaps with an s orbital of the hydrogen, and this one overlaps with the s orbital, okay, sorry, let me not use this part. Okay, so this two is in fact one sp orbital in this direction and one in this direction. And when this orbital overlaps with a s orbital of the hydrogen, and this one overlaps with a s orbital of the other hydrogen, you can see that the bond angle of the HCH will be 180 degrees. The other way we can remold the orbitals is that we take one of the s orbitals and we take two of the p orbitals and we remold them. So like one of the s orbitals and two of the p orbitals, and we remold them. When we remold the orbitals, they all always come out to be the same shape. You always have a bigger loop and a smaller loop. And the only difference between the sp hybrid orbitals, the sp2 hybrid orbitals, and the sp3 hybrid orbitals is the direction in which the orbitals are pointing at. So again, the sp orbitals point 180 degrees apart from each other. The sp2 hybrid orbitals, on the other hand, point at 120 degrees direction away from each other. So like one of them will point in this direction, and one of them will point in this direction, and the other one will point in this direction. They're supposed to be the same size, and the separation of all the orientation of these three orbitals is at a separation of 120 degrees from one another. So of course, like now, if we overlap with another p orbit or another sp orbital here, and then this one overlaps with an s orbital of hydrogen and the s orbital of hydrogen, we'll be able to create the correct bond angle of 120 degrees. And this is a trigonal planar arrangement. What's the meaning of trigonal planar? Planar means flat. Okay, because these three orbitals are in a flat plane, and therefore it's a trigonal planar arrangement. This is the sp2 hybrid orbitals. The final possibility of the hybrid orbitals is the sp3 hybrid orbitals. For the sp3 hybrid orbitals, basically we use one of the s orbitals and we use all of the p orbitals. And of course, if we use 4 orbitals for the remolding process, we will end up with 4 sets of sp3 orbitals. And again, the shape of each of the orbital is, again, there's a big loop and a small loop. And for each of these orbitals point at a orientation of 109.5 degrees away from one another, such that if this orbital overlaps with the s orbital of hydrogen, each one of them overlaps with the s orbital of hydrogen, we will be able to achieve a bond angle of 109.5 degrees for the methane molecule, as for this case. Okay, so I hope that you have a clearer understanding of what's the meaning of hybrid orbitals. They are basically reformed orbitals by combining a certain number of, okay, not a certain number of s orbitals, because you always have to combine one s orbital with a certain varying number of p orbitals. And again, the goal is to achieve the correct bond angle of the various molecules. So one thing that I forgot to mention is that for the sp orbitals, right, because we took one of the s orbitals and one of the p orbitals for the remolding effect. But notice that because for a carbon atom, it actually has one s orbital and one p orbitals, right? Which means that there's actually 2 unhybridized p orbitals. Unhybridized p orbitals. The meaning of the word unhybridized p orbitals means that they are not used for the remolding process, right? Because we only use one of the s and one of the p for the remolding, so 2 of them is untouched. So what are the orientation of the remaining 2 p orbitals, right? The remaining 2 p orbitals, one of them is in this direction, and the other one is in this direction. And these 2 will be used for sideway overlap, which will form the remaining 2 pi bonds of the triple bond in the molecule. So later we'll talk about this, which is in the ethyl molecule. For the sp2 hybrid orbitals, on the other hand, because we use one of the s orbitals and 2 of the p orbitals for the remolding process, which means that there will be 1 unhybridized p orbital. And this unhybridized p orbital will be used for sideway overlap to form one of the remaining double bonds. So this is a trigonal planar arrangement, and the p orbitals is perpendicular to the trigonal planar arrangement of the 3 sp2 hybrid orbitals. And this one will be used for a sideway overlap, which will form the remaining double bond. Okay, so to figure out the hybridization of orbitals of each atom, we count the number of single bonds and lone pair of electrons around the atom. Okay, so if we have 4 single bonds and 0 lone pairs, it will mean that there is actually 4 electron domains around the central atom, and it will mean that it's a sp3 hybrid orbitals because all of them are single bonds. So the important thing is how many single bonds, how many electron domains are there in around the central atom. If the number of electron domains around the central atom is 4, such as for this 2, right? Because like 4 and 0 and 3 and 1 lone pair, they are all 4 electron domains. If it's 4 electron domains, it will always result in a sp3 hybrid orbitals because we need 4 orbitals to point in the correct orientation to be able to accommodate the 4 electron domains. On the other hand, if we only have 3 electron domains, such as this case and this case, oh, sorry, this is not 3 electron domains. This is 3 electron domains. 2 plus 1. We need to have the sp2 hybrid orbitals in order to accommodate the 3 electron domains in a trigonal planar arrangement. This is actually 4 electron domains because it's 2 plus 2. The last possibility is that we only have 2 electron domains, which is 2 single bonds and no lone pairs. Then if we have 2 electron domains, then we would actually require the hybridization to be sp hybrid orbitals so that they point at an angle of 180 degrees apart from one another. So again, the double and triple bonds are formed by the remaining overlap of the unhybridized p orbital. So let me give a pictorial view of the ethene bonding molecule and the ethyl bonding molecule to derive from this point. If you look at the ethene molecule, because ethene looks like this, so the bond angle must be 120 degrees. And if you look at the carbon electron domains around this carbon, there is 3 electron domains, which means that it must be a sp2 hybridization so that we can have the hybrid orbitals pointing at 120 degrees apart from one another. So these are the three orbitals that's pointing 120 degrees apart from one another. The overlap of this sp2 orbital with this s orbital of the hydrogen will form this CH bond, and the overlap between the s orbital of this hydrogen and this sp2 orbital will result in this Hc sigma bond. It's a head-on overlap, I remind you. This sp2 overlap, sp2 orbital will overlap head-on with the sp2 orbital of this carbon to form one of the sigma bond. But again, I remind you that because it is the sp2 hybridization, right? One of the p orbitals is actually unhybridized, and this is the unhybridized p orbitals. Okay, and it will sideway overlap with the unhybridized p orbital of the neighboring carbon atom, and this will result in a pi bond. And hence, between this carbon and this carbon is one sigma bond, which is formed by the head-on overlap between the sp2 orbital and the sp2 orbital, and the sideway overlap between two of the unhybridized p orbitals, and hence we have a double bond, one sigma bond plus one pi bond, which will form the ethene molecule. The ethyne molecule, on the other hand, it's this molecule, and it has two electron domains around the center about this carbon atom, and hence the hybridization will be the sp orbital. And the sp orbitals point at an angle of 180 degrees apart from one another. I remind you again, these two yellow orbitals, there is not one p orbital, but it's actually it's not one p orbital, but two sp orbitals. One of the sp orbitals will overlap with a s orbital of the hydrogen, and in doing so, it will form the Hc sigma bond. And the overlap between this sp orbital of this carbon and the sp orbital of the neighboring carbon will result in a sigma bond between the C and the C. It will be one of the bonds in this C-triple-C bond. However, because if it's sp hybrid orbitals, right, there is two unhybridized p orbitals, and the two unhybridized p orbitals are both 90 degrees away from this set of sp orbitals, and one of this sideway overlap will result in one pi bond, and this other overlap, sideway overlap again, will result in the formation of a second pi bond. So this is one of the pi bonds, and this is the second pi bond. These are all sideway overlaps, and hence you have one sigma bond and two pi bonds, which will give you a total of a C-triple-C bond in the ethyne molecule. And on the at the end of the day, the ethyne is able to achieve the correct bond angle of 180 degrees for the molecule, which will maximize the separation of the electron domains around the molecule. Okay, so that's for the hybrid orbitals, and we have covered all the content for discussing orbital overlap for the formation of covalent bonds. So I just like to so there's one last point that I need to talk about to finish up this chapter, and we'll be looking at two past year A-level questions to illustrate this point. The bond lengths, November 2008, paper 1, question 19, the bond lengths in butyl-1,3-diene differ from those which might be expected. The carbon-carbon bond length in ethane is 0.154 nanometer. Okay, so like if you would, we haven't covered ethane, right? But the thing is that, so this is the structure of ethane. So what it's saying is that this CC single bond, it's 0.154 nanometer. And one point that I would like to make is that basically if the bond length is shorter, then the bond will be a stronger bond. For example, if it's a C-triple-C bond, right, the attraction between the nucleus and the three shared pair of electrons will be stronger, and hence they will be more closely attracted. If it's more closely attracted, the bond length will be expected to be shorter. So basically, like shorter bond length will imply that the bond is stronger. Okay, vice versa. If the bond is stronger, the bond length will be shorter. On ethene, in the other hand, is a C-double-C bond, and the bond length between a CC double bond is expected to be stronger than a CC single bond, and hence it is indeed shorter than that of a CC single bond. The central single bond in butyl-1,3-diene, however, is shorter than the single bond in ethane, 0.147 nanometers. So let us look at the structure of butyl-1,3-diene. This is the structure of butyl 1,3-diene. Between this carbon and this carbon is a double bond, and between this carbon and this carbon is a single bond. So if you were to use spectroscopic methods to measure the bond length of this CC single bond, you would actually experimentally get a bond length of 0.147 nanometers, which is actually shorter than that of ethane, because like ethane is also a CC single bond, right? So it's a fair comparison to compare the bond lengths of ethane, which is a CC single bond, with the CC single bond in butyl 1,3-diene. And if we do not know more, it should be expected that the bond length should be exactly the same because they are both CC single bonds, right? There's no reason for one CC single bond to be shorter than the other one or stronger than the other one, because all we have covered so far is that a triple bond is stronger than a double bond, which is stronger than a single bond. We have not made any mention of why is it the exact same two single bonds can differ in bond strength or bond length. Okay, so the question is, what helps to explain this C2, C3 bond length? If we were to look at the overlap of the orbitals between this carbon and this carbon in forming this CC single bond, and we were to look at the hybridization of this carbon, how many electron domains are there around this carbon? The answer is 3, right? There's one electron domain here, one electron domain here, and one electron domain which is between the C and the H. And there are no lone pairs, which means there's a total of three electron domains around this carbon atom, which means that the orbital that is used for overlap to form this CC single bond is a sp2 orbital and a sp2 orbital. Whereas if we look at the ethane molecule, right, this carbon actually has 4 electron domains around this carbon, 1 electron domain, 2 electron domain, 3 electron domain, and 4 electron domains, which means that the hybridization of this carbon is actually sp3, and the hybridization of this carbon is actually sp3. So the overlap of an sp3 orbital and a sp3 orbital of this carbon results in the formation of this CC single bond in ethane, whereas the overlap of a sp2 orbital on this carbon and a sp2 orbital on this carbon resulted in the formation of this CC single bond. So this is between an sp2 overlap. This is between an sp3 overlap. And so what's the difference, right? Remember when we studied ionization energies, we said that the s orbital is closer to the nucleus. Closer to nucleus than the p orbital. And that's the reason when you do the ionization energy, right? Like there is an anomaly whereby this one is because the electron is, this one it's like ns1, ns2, and this one is ns2, np1. This electron is removed from the p orbital, and the p orbital is arranged further away from the nucleus than the s orbital, and therefore it requires less energy to remove. Okay, I hope, like, if you don't remember this, just go and have a look at my lecture on atomic structure, ionization energy. Okay, so anyways, the s orbital is closer to the nucleus than the p orbital. If you look at the sp3 orbitals is formed by mixing one s orbital and 3 p orbital, right? So if you were to count the percentage of s character, which means that what is the percentage of the orbitals of the sp3 orbital that is formed using a s orbital, right? It's 25%, right? Because like you use one s and we use 3p, right? So it's like 1 over a total of 4 orbitals. That is the s orbital that is used to form this orbital, which will give you 25%. So it's 25% s character. Whereas for the sp2 orbitals, it's 1 over 3 percentage of s character that is used to form the sp2 orbital. And this is 33%, which means that the 33% of s character in the sp2 orbital is actually closer towards the nucleus. So what it means is actually that, right, the sp2 orbital is actually shorter as compared to the sp3 orbital, because of the fact that this is 33% s character. So it will be, it has a higher percentage of s character, which is closer to the nucleus, and this has 25% s character, which means that it will be further away from the nucleus. And this is the reason why, if you have a higher percentage of s character, it will actually be a shorter bond length, because you're using more of the s orbital in the building of the hybrid orbitals. Okay, so the answer to explain why this one is actually shorter than that of expected in ethane is because it's an sp2 overlap instead of an sp3 overlap as in ethane. Okay, it's an sp2 sp3 overlap. This is wrong because it's sp2 sp2. The electrons in the filled p orbitals on C2 and C3 repel each other. This is not relevant because the unhybridized p orbital of this carbon overlaps with the unhybridized p orbital on this carbon, whereas this one overlaps with this one, so it does not repel. The sp3 bonding is put shorter by a pp bond overlap. There is actually not even a single sp3 bonding, so this cannot be true. Okay, so the answer is A for this question. The bond lengths in propyne differ from those which might be expected. November 2010, paper 1, question 19. So this is a very similar type of question. In fact, it's the same type of question. So we're just going to learn what we applied in the previous question. So the carbon-carbon bond length in ethane is 0.154 nanometer. So again, like ethane is like this, 1, 2, 3, like this. And these are all hydrogens. So that is 0.154 meters between the carbon and the carbon, this one, as in the same as previous question. In ethyne, it's 0.12 nanometers. So obviously, this one will be shorter because of the fact that it's a C-triple-C bond. So it's indeed shorter than the ethane. The single C2, C3 bond in propyne, however, is shorter than a single bond in ethane, is 0.146 nanometer. So if we look at the structure of, so we are talking about this bond, which is a CC single bond again. If it's a CC single bond, we should expect it to be the same bond length as the ethane. Okay, however, this is actually shorter. If we look at the hybridization of this carbon, it has 2 electron domains. So the hybridization of this carbon is sp, and this carbon on the other hand has 4 electron domains around this carbon, one which is here, and the other 3 which is each one remaining between a C and a hydrogen bond. So this carbon is a sp3 hybrid orbital, and the overlap of this CC single bond is between an sp orbital and sp3 orbital, but for ethane is between a sp3 and sp3. So again, if you talk about the percentage S character of this sp orbital, it's actually 50% S character, and therefore it will be shorter than the sp3 orbital as compared to that in ethane. And that's the reason why it explains that this bond length is actually shorter in propyne, because it is a sp and sp3 overlap instead of a sp3 overlap in ethane. Okay, I hope that you understand this concept about the percentage S character that decides whether is it closer to the nucleus or not. Okay, so again, the learning outcome is to describe covalent bonding in terms of orbital overlap. So in order for covalent bond to form, orbitals need to overlap, and they will put the electrons in the overlap space in order for the covalent bond to form. However, certain molecules are unable to overlap in the way that they will form the correct ideal bond angle. So they need to use a S orbital and mix it with different numbers of p orbitals to arrive at a hybrid orbital, so that the hybrid orbitals can then overlap to give the correct orientation, so that they can overlap to form the correct bond angles, the ideal bond angles of any given molecule. Okay, I hope that in this lecture you understood more about covalent bonding and the overlap of the orbitals and the hybridization of the orbitals. So if you have any questions, you can drop them in the comment section. If you like the video, please help me hit the like and subscribe button. And I'll be covering the next few learning outcomes in the next few previous lectures in the topic of chemical bonding from JCH to chemistry syllabus. So see you again, and stay tuned for the next few lectures. Bye-bye.